So groups 1, 2 and 3 like to lose electrons to form ions. Well, let me circle groups 1, 2 and 3. It's those vertical columns there. And in purple, I'm going to separate the metals from the non-metals in this part of the periodic table. And you can see that groups 1, 2 and 3 are essentially all metals, except for maybe boron and hydrogen. So metals are electrophobic. They like to lose electrons. Now, that seems strange that I've highlighted those non-metals there, group 0, but elements in groups 1, 2 and 3, and 5, 6 and 7, as we'll see a bit later, they want to form ions with the electronic configuration of the noble gases. This is a hugely fundamental part of chemistry, that the noble gases have stable electronic configurations, and that's what other atoms try to attain. Now, instead of saying same as noble gas, we can say isoelectronic. That means the electronic configuration is isoelectronic to a noble gas. Iso, same, electronic, electrons. So the same electrons. Now these groups 1, 2 and 3 form ions. Since they're metals, what do metals do? Oh, I've lost them there. Metals like to lose electrons. So metals form ions by losing electrons. Again, hugely fundamental. Let's choose potassium. The atomic number is 19, which means it has 19 electrons. And if it can lose one, it will have 18. And that's the same as argon, isoelectronic to argon. If potassium loses one electron, then it will be isoelectronic to argon. So it's going to be stable. Potassium will become stable and an ion if it can just lose one electron. Now, we put square brackets around argon, which also means isoelectronic to argon, the same electron configuration as argon. Let's dig a little deeper. So there's potassium, electrons, protons, and neutrons. And you can see it's got four shells. 2, 8, 8, 1. So if potassium can lose that one electron, it will look like argon. It will have a full outer shell. And that's what these things are trying to do. These atoms are trying to attain a full outer shell, which is intrinsic stability, just like the noble gases. And so that outer shell is full with 8. Smash it. Now potassium only has 18 electrons now. It used to have 19. And so it has a positive charge. It's lost a negative. You could add the charges up if you want, and that comes out at plus. Smash it. Square brackets means isoelectronic to argon. Well, that was the long-winded explanation. Let's go a little faster now. Let's choose magnesium, atomic number 12. It has 12 electrons. If it can lose 2, it will just have 10 electrons. It will look just like neon in terms of its electronic configuration. Now that's an equation, so it needs to be balanced. I'm just going to stick 2 electrons on there for completeness. Aluminium, 13 electrons. If that can lose 3, it would have the same number of electrons as neon. And that's the ion is going to have lost 3 electrons. So aluminium atoms like to lose 3 electrons to become more stable. Isoelectronic to neon. Now maybe you're seeing a pattern here, which is good, because the periodic table is all about patterns. Group 1 metals lose 1 electron to become an ion. You probably noticed that group 2 metals are going to lose 2 electrons to become an ion. And group 3 metals are going to lose 3 electrons to become an ion. And what was the charges of those ions? 1 plus, 2 plus, and 3 plus. Well, that's quite a nice pattern there. It doesn't apply to group 4 because they tend to share electrons, covalently bond, not ionically bond. Well, what about gallium? If that loses 3, it's in group 3, it's isoelectronic to nickel. And indium, if that loses 3, it's isoelectronic to palladium. You know what? The rule still applies. Group 3 metals are plus 3. In SO, we don't need to know why. It's to do with the d orbitals. What's that? You don't need to know. Just remember, group 3, still plus 3.